So far, we've talked about how to program our computer in C. Now we're going to switch over to programming a microcontroller. Let's do a brief review of the difference. So your computer probably runs at several gigahertz. That's billions of instructions per second. It probably has several gigs of RAM and maybe hundreds of gigs of memory. This is a PIC32 MX795F512H microcontroller. It's a 32-bit microcontroller, as opposed to your computer's probably 64-bit. This runs at 80 megahertz, so hundreds of times slower than your computer. It has 128K of RAM, so lots less RAM, and it has 512K flash, so that's the space for the program itself. So not very impressive compared to your computer, but it only runs one program. So we'll write our code on our computer. We will cross-compile it, so that is compile it on our computer, but for a different CPU. So the code we compile on our computer wouldn't run on the computer. It can only run on this board. We will download the executable onto this board, and then when it runs, that's the only thing that runs. So it will actually be able to read the voltages on these pins digitally, perhaps several million times per second. So it can actually do things much faster than your computer because it doesn't have anything in the background that it has to worry about. Now, the microcontroller itself is this center big chip, but it comes in a package that's not very usable, unless you have very special kinds of soldering equipment. So this board, which I call the NU32, is what we call a breakout board. It is a printed circuit board with the accessories necessary to make this microcontroller work. So one thing you can definitely see is that it's got lots of pins along the side. That's where we can plug in buttons and sensors and motors and things like that. It's got two LEDs that are labeled LED 1 and LED 2 built in, so we can immediately flash some LEDs without having to build a circuit. It has two buttons, a reset button and a user button. The reset button is hardwired to a reset pin on the microcontroller, so if you push that, the PIC stops whatever it's doing, and then when you release the button, it immediately starts the code over again. So that you don't have much control over that. But the user button is just wired to some pin, and so we can decide whether we want to read that pin or not. There's a little silver chip next to the PIC. That's the crystal resonator that goes at 8 megahertz. So that goes as an input to the PIC, and the PIC turns that into 80 megahertz. There's another little black chip next to the PIC. So the PIC is capable of talking USB to this micro USB connector on the end of the board. But rather than use the USB module to talk to your computer, the PIC talks what we call UART, or serial communication, to this FTDI USB to serial converter, and this chip talks to the mini USB port, which is what we primarily use to program and debug the PIC. So the code comes in over USB, gets turned into UART, and then dumped onto the PIC. We don't use power from the USB port, though, just in case you accidentally touch like a battery voltage to the power pin on the PIC. We don't want to damage your computer through the USB cable. So instead, all the power comes from a DC connector right here. And there's a slide switch which turns everything on, and a red LED that indicates if power is on. Should you ever turn your board on with the slide switch, but notice the red light doesn't come on, that usually means you might have a short on your circuit somewhere. So always double check your circuit before you turn it on. If you do turn it on and that light doesn't turn on, turn it off quickly before anything gets hot and burns out. So how does the power system on the board work? We'll flip it over. And we have two voltage regulators on the bottom. One takes the voltage in from the DC jack and makes 5 volts. The other takes the 5 volts and makes 3.3 volts. And then the PIC is powered by the 3.3 volts. And most systems that we use nowadays run on 3.3 volts. Now, traditionally, 5 volts was very popular, so we still provide 5 volts through one of the pins. And someday 1.8 volts will be standard, so things are constantly changing. Now, this board usually doesn't come like this. It comes in a breadboard, which is our rapid prototyping for electronics board. So that would look like this. And there's no reason for you to really ever take your NU32 out of the breadboard, but I wanted to show you what was on the bottom of it. I'm going to stick this one back into its breadboard. It's a little hard because there's so many pins. Now you'll notice that this board it's got one button, 2 LEDs. It doesn't have a keyboard, it doesn't have a screen. So at some point we'll deal with how to talk to this 16:2 LCD screen. And then for text input, we'll be using our computer to send data back and forth through the USB cable. So we're going to be reviewing this hardware a lot more. Let's do a quick start on the software to see what do you need on your computer to be able to compile code and send it to this board. So this will vary depending on whether you're on Windows, Linux, or Mac, but it should always basically look the same. On our website, we have a zip file that has information from every single chapter of the book. So you'll want to download that and store it somewhere. I put this pretty close to the root of my system so I don't have to CD many times when trying to find it. And the first thing that we want to do is inside of this chapter 01 quick start, we want to copy all of that content into wherever our working directory is going to be. So I've got a folder called skeleton, a C file called Nu32 utility.c, and then simplepic.c and talkingpic.c. The first thing we need to do is we need to turn Nu32 utility.c into an executable. So I've already done that here. But let me show you how to do it. So this is the last C file that we'll probably need to use on our computers that's not specifically made for the PIC. So this is the last time we'll use real GCC. So I'm in my folder, and I can see that I've got this Nu32 utility.c file. And to compile it, I'll use GCC and Nu32 utility.c-o. And I'm going to call it Nu32 utility. So I'm going to overwrite the previous one I did. And then on Windows, I need to tell Windows when it compiles this to use a special library for serial communication, and that's lwinmm. So an additional dash. That's not necessary on Mac or Linux. Okay, so that was compiled. And now I have an executable. I could call that from here, Nu32 utility. And so when this program runs, this is called a bootloader. So a file that we compile on our computer and we need to send to the PIC, we'll use this program, the Nu32 utility, to send that file over. And then the PIC will self-program itself with that file. This program needs two inputs. It needs to know what is the COM port, so that is the name of the USB port that the Nu32 is using, and it needs to know the path to the file we're trying to upload. That type of file is called a hex file. Now, you'll do that once, but eventually you won't need to do that. You'll never call this. We're going to use a special program called make, and make will be in charge of calling this program for us after our compilation has been done. So let's take a look back to our files again. So back in my folder, I've got a folder called skeleton, and skeleton contains the 4 files that every project will do needs as a bare minimum. Nu32.c and h, those have helper functions that have variables stored in them that are specific to the Nu32. The bootloader.ld file is a linker script that tells the GCC compiler for the PIC where to specifically put the code when it installs it on the PIC so that it doesn't overwrite our bootloader. So your PIC comes pre-programmed with a program called a bootloader so that the PIC can self-program itself, and we need to make sure we don't brick our PIC by accidentally overwriting that. So that's what the bootloader.ld file does. And the last thing is a make file. The make file is no extension. And that's kind of like the most complicated part of all this. So let's take a look at the make file. So I've opened this folder in Visual Studio Code. And when you first open it, all of these variables at the top will be blank. And it's your responsibility to fill them out with paths that are specific to your computer. So the first one is, where is the compiler installed? And this is the specific GCC compiler that comes from Microchip, called the XC32 C++ compiler. On my computer, installed the program files Microchip, XC32, the version number, and then inside of a folder called bin. Bin stands for binary. You'll actually see lots of executables in there that have to do with GCC, and we'll play around with a bunch of them as we go on. The next one you can leave blank. Harmony is a set of what we call middleware library files that we won't end up using in this class. So you can download Harmony if you'd like. It's a couple gigs, but we won't need it, so you can just not fill that out. The next thing is the NU32 Path. This is the folder that contains the NU32 utility program that we just created. So copy your path to that location there. Then you need to know the name of your board, and it might vary from how many times you've plugged in this kind of board to your computer. So we'll figure out how to find out that number in a second. And the last thing is we need a program that lets us send and receive text over the USB port. On Windows, we'll use a program called PuTTY. So you'll download and install PuTTY and then put its path here. If you're on Mac or Linux, you'll just type the word screen, which is a program that comes on your computer. You don't have to put the full path. You just type the word screen. So that's how you set up your makefile. The next thing we want to do is compile some code for the PIC using that makefile. So back in our folder, we'll go back one. Now whenever I want to start a new project, I will copy my skeleton folder and paste it. And the first program I'm going to write is called SimplePic. So I'm just going to call it simple. And I will drag simplepic.c into simple. And while I'm here, I'm going to make another version of skeleton that I will call talking. And I'll put talkingpic.c in there. So if we look at simple now has the makefile, the nu32.cnh, and the bootloaded. Every project we have will always have those 4 files. And then my main function is in simplepic.c. And then I can add more and more helper C and H files in here as I need them. So let's go into simplepic and compile it from the command line. So I will cd into simple, and we can see that I've got those 4 files. And the way that I compile this, the book will explain to you how to do this manually, and you'll do that once. But from ever on after that, we're going to use the program make to do this for us. So make opens anything called makefile in the folder that we're in, and interprets that language in the makefile to do the compilation process for us. Now on Linux and Mac, make is already installed. If you're on Windows, you're probably using mingw to install GCC, and that comes with its own version of make. So to call make from here, I have to type mingw32-make. Or you could install make on your Windows computer and not have to type mingw32. So I'm using mingw32, so there we go, mingw32-make. I hit enter. So that program, which is on my path, and that's why the computer is able to find it and locate it, just like if I type GCC. It opened the makefile, and it followed the instructions there, and it compiled my C code into an executable. So how do we know that? I can type dir, or if you're on Linux and Mac, ls, and we can see that the 4 files I had in here have been turned into many more. I've got nu32.o, simplepic.o, so that's the object code, the the space for it hasn't been linked yet, so that's the object code. Then the LD file was used to create the elf file. The elf file is every bit of memory inside of the PIC, what it should contain. And then that gets compressed into the hex file, which is the program itself that we will send to the PIC over the cable. And then we've got this cool map file, which if we investigate will show us where all of our code went in memory. We'll investigate that a lot. And a disassembly file, which is the C code turned into assembly, and we'll be able to see exactly how our C was turned into assembly. That'll be pretty neat. We'll do those things later. Okay, so now I will plug in my PIC, and we'll figure out how to read the COM port number and then put the hex executable code onto the board. Okay, so back to the PIC. I need to plug in the mini USB cable. and the power supply. Okay, plug those in. When I turn on the power switch, I get my red LED. And I've tested and pre-programmed all of these NU32s, so the program that's on there right now will turn on a single LED. So let's figure out, how do we know what the COM port name is for this board? There's a bunch of ways to do that, but a simple way on Windows is to type mode and hit enter. And for some reason, this takes a few seconds to run. The equivalent command on Linux and Mac is ls/dev/tty.star, or something similar for Linux. And here we see sometimes you have a bunch of ports. In this case, I only have one. It's COM8. So on my makefile, I typed COM8 for the port number. Okay, there's one more thing I need to pay attention to. When the PIC first turns on, it's running the bootloader program. The bootloader program says if you're not pushing the user button, immediately start running the code that's there on the board. So it's immediately started to run my program. If I want to overwrite that program, I need to put my board into bootloader mode so that the NU32 utility program can be used to send the new program and overwrite the old one. So how do I put the PIC into bootloader mode? I need to be holding the user button when the PIC turns on. So if I push the reset button, and then while I'm holding it, push the user button, and then I'll let go of reset. Now when the PIC turned back on after resetting, I'm still holding user, and we'll see that LED 1 is flashing. That means the PIC is in bootloader mode, and it's ready to receive data from the NU32 utility. So another way I could do that is I could turn off the board. I could hold the user button while I turn on the board, and it will go into bootloader mode. If I'm ever in bootloader mode and I don't want to be in bootloader mode, I could hit the reset button, and my program just starts to work. And eventually you'll get so used to this that it's a rolling action. Push and hold reset while you roll over to user and then let go of reset. Okay, so let's now load our code using the utility, and we'll use the makefile for that. So I'm going to use mingw32-make space write, and that's a command for the makefile that instructs make to use the NU32 utility to send this hex file. So I'll hit enter. This is a pretty short program. The hex file is only 320 lines, so it went very, very quickly. Zipped right through, and now my program is running on the PIC. Simple as that. This particular program, simple, flashes the LEDs back and forth. And in another video, we'll review that code to see why it's doing that. It also pauses if you push and hold user. So if I let go flashing, push and hold user, stops. If I hold reset, the PIC is in reset. The power is still available, but the PIC is not running code until I let go of reset. It starts again. And then I can go to bootloader mode, and let's write another piece of code. Let's write talking PIC. So I'm still in my folder simple. Oop, there we are. So I'm going to go back, and I had already copied skeleton and renamed it talking, and put talking PIC in there, so I can cd into talking. And I can do the same thing. I can do mingw32-make, and that will compile. Now, if we had typed some code and we had made some errors, this is where we'd see errors similar to when you use GCC and code didn't compile. This was pre-made, so we expect it to work. So I can do dir to make sure it's all there. And then I could do mingw32-make write. And my single LED is blinking, so I know it's ready. So I write that program over. Now I'm running, the code is responding to text input from my USB cable. So from mingw, I can type putty, or if I'm on Linux or Mac, screen. And that's going to open up putty or screen, the program. and allow me to communicate using text. So I'm going to quickly just add this to my video capture. Need a window capture. And we're going to be capturing PuTTY. So PuTTY looks like a terminal. But it's a terminal that doesn't show anything you type. It only shows anything that is sent back over the USB cable from, in this particular case, COM8. This particular program, Talking PIC, and we'll review that in the next video, says if I ever receive any data and then the enter key, I will send it back. So if I mash my keyboard, all these letters are being sent to the PIC, but the PIC doesn't respond until I hit enter. And when it does, it sends all those characters back. So I can type stuff and enter and stuff and enter and stuff and enter. You could hit enter a bunch of times and blank lines get sent back. And you'll notice that the LEDs are programmed to invert every time we hit enter. So each time I hit enter, we see the LEDs flick back and forth. And when I'm done, so I can use PuTTY to do all kinds of interesting debugging and data input. I can just close PuTTY and go back to my terminal window and continue to edit the code and so on. Now, exiting screen is a little more difficult. You hold Control A, Control K, and then type Y to exit screen. So we're going to practice this a bunch, and you'll get used to putting your PIC into bootloader mode, using make to compile your code, and make write to send the code, and make PuTTY or make screen to communicate with your board.